And welcome again. And you can see one more problem at your screen. And this problem statement is two identical homogeneous rotating bodies of a spherical shape with mass m and radius r, both are identical, move towards each other with the same magnitude of velocity v naught. The angular velocities of rotation of the bodies omega 1 and omega 2 form an angle alpha, then that means their angular velocities are at an angle alpha and are equal in magnitude. Both have equal magnitude omega naught as a result of a head-on inelastic collision. Head-on inelastic collision. One body of the same density is formed, the shape of which can also be considered spherical, right? So determine the angular velocity omega of the rotation of the resulting body and change in kinetic energy of the system. We can say that in this problem, two bodies merge to form a third body, and before they merge, they are rotating with an angle between their angular velocities. So we will need to imply the conservation of angular momentum, and to do this we have to make a choice of a proper axis of rotation, and this is going to be the key thing to decide in this problem. And I would like to choose the common center of mass of the system, which is at rest, of course rest, since the principle of conservation of linear momentum is also applicable here, and both the bodies had equal linear momentum in opposite direction before the collision, and that means that leads us to the total linear momentum of the system is zero before the collision. So the center of mass is at rest, and it will remain at rest after the collision as well, because the principle of conservation of linear momentum is applicable. And you can observe one more thing simply by looking at the nature of the collision itself. It is head-on collision. So the velocity of the bodies before collision are directed along the line on which the center of mass of the system is located. You can think something like this. Wherever be the center of mass of the system, their velocities are like this, and this is the common center of mass of the system I was talking about. And you can also observe one thing, that the moment of momentum caused due to the translation of bodies is zero about this axis. This is an axis passing through the center of mass, common center of mass of the system, and that means the angular momentum of each of the bodies under consideration relative to the center of mass of the system of bodies is equal to the sum of spin angular momenta before and after collision. And we cannot use the conservation of kinetic energy in this case, because kinetic energy is going to be changed because the collision is not elastic. So let's plan the solution, and the first part of the solution is what I can say in a strict mathematical terms, that system of two bodies in this problem is isolated system of the two bodies. Consequently, the total momentum of the system and total angular momentum in the lab inertial frame, which is related to the earth, which is at rest with respect to the earth, are conserved. So we could write the first principle, conservation of linear momentum, that is nothing but mv naught minus mv naught equal to 2 mv, and this says v is equal to 0. Therefore, the motion of the resulting body is purely rotational. It has got no translational velocity at all after the collision. And we can also write the law of conservation of angular momentum of the system of bodies with respect to the common center of mass just before and after collision, and it will be something like L1 plus L2, that is equal to L. L1, L2 are the moments of momentum of the first and second body before the collision, and L is the moment of momentum of the resulting body after the collision. And we can also write the h of the spherically symmetric bodies. L1 and L2 are the angular momentum of each of the spherically symmetric bodies relative to their own centers of mass, and that is the spin angular momentum. So that we can write here L1 equals I naught. Both are having same moment of inertia, so I naught omega 1. Let's their magnitude are same, and L2 equals again I naught omega 2, and L is of course the final moment of inertia after the bodies are getting merged, multiplied by its angular velocity. And using these two equations, this equation and this set of equation 2, you can see here that omega is simply I naught by I omega 1 plus omega 2, and to find omega 1 plus omega 2, we have already some informations like omega 1, magnitude of omega 1, magnitude of omega 2, both were same before the collision, and that was equal to omega naught, but there was angle between omega 1 and omega 2, and the angle between omega 1 and omega 2 was clearly equal to alpha. So you can convince yourself that you have got two vectors, or two vectors like this having an angle alpha between them. This was simply the name of your first vector, that was omega 1, omega 2, and their sum will be like this. And you can see here this angle is pi minus alpha, and these two angles beta will be same because these omega 1 and omega 2 are of equal magnitude, that is equal to omega naught. And you can use simply the sine formula and get the result that omega will be equal to 2 omega naught cos alpha by 2. But I should have made a mistake here, because there was nothing about omega that was given in this problem. We found out we have this relation we had this relation. This was the original relation. So that we should have written here something like I naught omega 1 plus I naught omega 2 equal to I omega. So from here we got omega equals I naught upon I omega 1 plus omega 2. So by adding two vectors like having magnitude I naught by I naught by I omega 1 and I naught by I omega 2, and the angle between them is equal to alpha, so that you can get here omega, and use the same principles like these two angles are same because these two have equal magnitude. Omega 2 is also equal to omega naught and omega 1 is also equal to omega naught, so these two angles are same, and this angle is pi minus alpha. You can use the sine rule and you will get omega equal to simply 2 omega naught I naught by I cos alpha by 2. So and how can you find I and what is I and what is I naught? So I naught was basically, they were spherical balls, so I naught was basically 2y5 mr square, and I you can write in simple manner 2 by 5. This is the third body formed after merging of both the bodies, so their mass will become 2m, and suppose that its radius is r, then you can write its moment of inertia in this manner. And to find the value of r, you know what to do. That is their densities are same. That means density to volume, density multiplied by volume is equal to mass. Because density is mass per unit volume, so mass is equal to density multiplied by volume. So and their densities are same, so you can write compare their volumes, and you can write twice of 4 by 3 pi r cube. The volume of both, the volume occupied by both the spheres is equal to will become equal to 4 by 3 pi r cube, the final sphere. And so you can get here the value of r, and you got everything, the value of omega here, omega from here. By just putting the values of I, you can get it here. And the changes in kinetic energy, you can write like final kinetic energy, that is half I omega square minus initial kinetic energy. The initial kinetic energy was the initial kinetic energy consists two kinds of kinetic energy, translational as well as rotational. So for both the bodies, you can simply multiply it by 2, and you can write the translational kinetic energy simply like this, and rotational kinetic energy, this was omega naught, and you will get the change in kinetic energy as well. So I think the problem can be solved by putting the respective values, and you can obtain your result. Thank you very much for watching.